For this example, we're going to look at the elliptic cone, x squared over 4 plus y squared over 9 minus z squared equals 0. Notice that would be equivalent to bringing the z squared to the other side and saying x squared over 4 plus y squared over 9 equals z squared. Probably a little easier for us to think of it that way. And let's first take a look at what happens if z equals 0. So where does this intersect the plane where z equals 0? And that, of course, is the xy plane. What does that intersection look like? Well, if z is 0, I have x squared over 4 plus y squared over 9 minus 0 squared equals 0. X squared over 4 plus y squared over 9 equals 0. What is that? That's just a single point. The only intersection we get there is the single point. So in the xy plane, when this surface intersects the xy plane, the result is simply the point 0, 0. Now, let's take a look at what happens if y equals 0. So if y equals 0, that is what? That is intersecting the xz plane. And let's think about that for a minute. X comes out here, y goes up there, z goes there. So the xz plane is the left side, if you will. Looking at it from the left, what are we going to be seeing? And so if y equals 0, that goes away, and I just get x squared over 4 equals z squared. And then taking the square root of both sides, I get z is plus or minus x over 2. So those are intersecting lines. Do we see that? Z equals x over 2. Z equals negative x over 2. So intersecting lines like this, essentially. So looking at it from the left, it's going to look that way, and from the right, it's going to look similarly, yes? So if I let x be 0, now I'm looking at the yz plane, which is sort of a front view kind of thing. So if x equals 0, what do we get? We get y squared over 9 equals z squared. So z is plus or minus y over 3. So again, we have intersecting lines. Now, is this enough for you to visualize what's happening here? Can you see what the shape is going to look like? I'll add one more little piece here. What about in the event that z equals 1? Or if you like, z equals negative 1, it would work the same way. If I replace z with 1 here, what do I get? I get x squared over 4 plus y squared over 9 minus 1 squared is 0. X squared over 4 plus y squared over 9 equals 1. And that, of course, is an ellipse, hence elliptic cone. So as we move up in the z direction, in both of these cases, z is up, the trace is going to be an ellipse. Does that give you a chance to visualize what this looks like? So as we put all these things together, what does our elliptic cone look like? So let's pull up an image. So here's our cone. Notice the xy plane, we have x in the red direction, y in the green direction, and the intersection is indeed a single point. We see that point 0, 0. And you see the ellipse when we have various values for z. So as z grows, this is a z of 2 that they used. Notice we can see that we have 2 ellipses there. And do you see the intersecting lines? Looking at it from this perspective, we see a pair of intersecting lines. And looking at it from this perspective, we see a pair of intersecting lines. And our result for that thing is what we call an elliptic cone. So we have this elliptic cone that is defined by that equation. Now, what did that equation look like? Equals 0, 1 positive, 1 positive, 1 negative. And what was our axis of rotation or our axis of symmetry? if we go back and take a look at that, the axis of symmetry is what? Is the z-axis. It's being wrapped around the z-axis. So let's call that the axis of rotation is the z-axis. So what would have to change for us to move from an axis of rotation as the z-axis to an axis, let's say, would be the x-axis or possibly the y-axis? So looking at our previous example, and I won't worry about the numbers on the bottom too much here. That just gives us the size of the ellipses we're dealing with. But this was our first example, and this had a z-axis of symmetry or axis of rotation. So notice, in that case, the z part was negative and the x and y's were positive. If I want an x-axis of symmetry, what would this have to look like? If I want an x-axis of symmetry, what do you think that's going to be? Well, the x guy is going to have to be negative and the other two will be positive. So just ignoring the bottoms, y squared plus z squared minus x squared equals 0 should give me an x-axis of symmetry. Let's take a look. Pulling up this app. Notice I have y squared plus z squared minus x squared is 0. And then notice it's wrapped around the x-axis. The x-axis of symmetry, that's where the thing is rotating. Also notice a single point here, and then we see those intersecting lines from these other perspectives. You see the intersecting lines there. So what if I want the y-axis to be an axis of symmetry? Okay, if that's my goal, I want the y-axis of symmetry. Then the y part would have to be negative, and the x and z would have to be positive. So something like this, x squared plus z squared minus y squared is 0 should give me a y-axis of symmetry for my elliptic cone. Let's go ahead and see if that's the case. Pulling this up, let's change it to x squared plus z squared minus y squared is 0. And can you see that indeed the y-axis is the one that it's wrapping around? You see x here, we see y coming out this direction. And if I want to put denominators in, I can, right? All this is going to do is change things a little bit. It doesn't quite look as nice as the other examples we've seen, but it certainly still fits the requirements of an elliptic cone with a y-axis of symmetry.